Hello everyone, this is Emil Naruto. Welcome to my channel. So, yesterday we have already talked about gradient descent. I mean, how do we use? I mean, what's the purpose of using gradient descent? We have already talked about that particular method. So, gradient descent is used. GD is used to pick the best fit line, right? So, what is a best fit line? So, best fit line is expressed as best fit line will be expressed in the format of y hat is equal to mx plus c. So, this is the line which is nothing but the our predicted model. Our model has predicted something that is nothing but this particular equation, that is y hat. Okay, that is the prediction. And now we already have the actual ones, right? We already have the actual result, that is mx plus c. Oh, sorry, that is y equal to mx plus c. This is nothing but the actual one. Okay, so best fit line is this particular equation, that is y hat. It is represented by y hat, and this is nothing but the actual one, right? This is the actual and this is the prediction one. Okay, so if you want me to plot this topic, plot this thing on a kind of plot, so how do I do that? So I'll have something like, okay, so this is the x-axis and this is the y. So this is my independent variable and y is my dependent variable. Okay, so if I take any kind of, I mean, we everybody knows that this is a linear regression model. So the relation between x and y is represented in the form of a linear kind of a line, that is nothing but the y equal to mx plus c, right? So so these are all the some kind of data points here. So these are the data points here. See, these are all the data points, and this is the best fit line. Let's imagine this is the best fit line. So what is the notation of the best fit line here? That is nothing but y hat equal to mx plus c, right? So just take any point on the x-axis here. For example, I have taken this point, this particular point on x-axis. Let's say this is something, some point, okay, x. So for if I can project this particular point onto our predicted line, what happens? So it's actually getting touched here. Okay, so at this point, so uh, if I can just project this particular point onto my y-axis, then what happens? So this would be the predicted line, that is this would be my y hat. Okay, for example y1 hat. Okay, but I also have the actual value. Let's say the actual value is this. Okay, this is the actual value. So if I can project this particular line onto my y-axis, then this would be my y1. So this is my y hat, that is the predicted line which my model has predicted, but this is my actual line. So this is the y1 here. Okay, so what happens is, see here, this is the predicted and this is the actual one, and there are such kind of there are so many kind of infinite number of lines. Okay, so there is a possibility of drawing infinite number of lines here, but out of all those infinite number of lines, this is our best possible best fit line. So that that best fit line, okay, that particular best fit line, out of all the infinite number of lines, are found by or found by gradient descent. Gradient descent method. Okay. So this is the thing here. Okay. So how to find that particular best fit line here? So how to find the best fit line? So if I have, let's see, for example, and I have the points here like this. Okay. So what is the possibility of drawing the best fit line? So this could be one kind of possibility, and this would be one kind of possibility. This is one kind of possibility here, another kind of possibility. So likewise, there are so many kind of the scope of forming the number of lines are nothing but the infinity. So we can form infinite number of lines here. So out of all these infinite number of lines, we want to pick the best fit line. So how to do that? So what we can do is we need to evaluate each of these lines, and we want to compare all of them with a certain kind of metric. So what is that metric? So with the help of that metric, we are gonna compare all the infinite number of lines, and we can choose the best fit line, right? So for example, what is that metric here? So first of all, we evaluate we evaluate each line on basis of some evaluation metric, right? So if you want to evaluate something, we need some kind of a metric, right? So that is nothing but, in this case, that evaluation metric is known as called average sum of square, average sum of squared errors. So this is that particular metric. So what is this sum of squared error and what is this average sum of squared error? I'll explain. Don't worry about that. Okay. So just look at this example here. So just look at the example here. For example, I have taken one kind of point here, that is this uh, maybe some kind of point. Okay. So for this particular point, let's say x1, this is the x, this is the y. Now for this particular point, so we already have, we know that this is the, so this is the let's say this is the best fit line, for example. And now what happens is, uh, so this is one of a line. Okay. And now if you can project this particular point here, what happens? So this would be the predicted one, that is y1 hat, you can call. So if you just project all the project this particular point onto the y-axis, then this would be, yeah, so this would be your y hat. This particular line would be your y hat, y1 hat. And if you want to look that where is my actual line, so your actual line would be somewhere here, okay, at this point. So if you can project this particular thing, then this is your y1, this is your actual one, and this is your predicted one, right? So for example, yeah, this is the thing here. Now what you can do is, how many kind of things will happen like this. For example, you can also have something like, if I can pick some kind of point like here at this particular, so I can call it as x2. So I want to project this particular point to my predicted model. So this would be my y2 hat. Okay, this would be my second predicted model, which is nothing but this. Okay, and also I want to know where is my second actual one. So my second actual one would be, for example, let's say this. Okay, so if I can project this onto my y-axis, then what happens? So this is my y2. So this is y1 hat, this is y1, this is y2 hat, this is y2. Okay, so now we want to know what is the difference between the actual result and the predicted result. So we want to know. So the difference between y1 and y1 hat, right? So we want to know the difference. See here, the difference. What is the difference here? So this is the difference here, right? And when you look at here, so this would be our difference here, right? So when you compare here, see the difference between y1 and y1 hat is uh, pretty much smaller. And when you look at here, the difference between the y2 and y2 hat is somewhat larger than the y1 hat, right? So you need to pick that particular line which is having the lowest, the least distance between y and actual and the predicted one. So we pick uh, the line which has the least difference between actual. I'm just saying in general, right? So I'm not mentioning y1 or y2 or something, right? This is the actual, so you can call it as the least. So we want to pick that particular line which has the least difference between the actual and the predicted one, right? So this is known as the best fit line, known as the best fit line, right? And okay, so this is the thing here. But so you need to, there are some infinite number of lines, right? So see here, there are infinite number of lines. Okay, for example, I'll tell you. So you have calculated, okay, you have calculated the difference between the actual and the predicted one for this particular line. Okay, so you have got some kind of value. Okay, and now you need to check another this particular line, and you have got some kind of squared error, right? You have got some kind of a value, and you will check this, and now this and this. So likewise you need to check all the lines, and you will decide that particular best fit line which is having the least sum of the squared error. So you will decide like this. So what you can do for that, you need to calculate the sum of the squared error for all the points of a particular line, and then you will continue this process for each of these lines. Then you will compare all the lines with the values. Then you will select that particular line which is having the least sum of the squared error, right? So I'll tell you. So what you can do is you just need to select. You just need to calculate the error for all the points. For example, this is a line. Okay, so this is a line, and we have some kind of points here, like this, like this. So you need to calculate the difference uh, between the actual and the predicted one for all the points for this line. And now you will also have this kind of a line, and also you need to calculate the sum of the squared distance, sum of the the distance between the actual and the predicted one for this particular line. So likewise you will calculate all you will calculate this. I mean, you will just repeat the process for all the possible infinite number of lines, and then you will decide upon which line is the best fit line. Okay. So what you will do is you will just calculate the error for all the points of the line, and you will sum up all the errors of the point of the line, and then sum of all the errors should be least. So I'll give you an example. Okay, so for example, if you can look here, I'm drawing something. Let's say, okay, so I have taken some kind of point here, and also let's see. Okay, so if I project this particular point onto my prediction line, so this would be my y hat. Let's say y1 hat, and if I want to know that this is my actual one. Okay, so this is my actual one, and the above y1 hat is my predicted one, right? So for example, I have taken a point like this. Okay, and if I can project here, so I'll be deciding that this would be my predicted one, that is y2 hat, and I also want to know what is my actual one. So my actual one would be something like this. So this point. Okay, so this is my y2. So if you want to know what is the value of it, so if you want to calculate the sum of the squared error for it, so what happens, you need to minus, see here, you need to subtract y1 from y1 hat. See, if I can subtract a y1 hat minus y1 here, so what happens, see here, the values will be starting like this: 0, 1, 2, 3, and so on in this. Okay, so the values are actually starting from 0 to, and it will goes on uh, to the highest position. So here my y1 hat is something kind of a bigger value, so it is the bigger value, minus I'm subtracting some kind of a small value. See, this particular value has, let's imagine this particular value has 3, but this particular value has 5. So 3 will be the smaller, right? So the actual value would be the smaller value here. So this is the small value. So if you subtract a small value from a big value, then what you will get? You will always get the positive value, right? So you will get the positive sign here. Okay. But when you calculate here the sum of squared, what happens? I mean, if you calculate the difference between this, what happens? So I want to calculate the difference here, like y2 hat minus y2. So what happens? So y2 hat is very much smaller, right? So this would be the smaller thing. Okay. So this would be the smaller thing, but I am actually subtracting y2 from y2 hat. So what happens? So y2 hat is uh, so this would be the smaller thing, because this is the small thing, right? And if I want to subtract from y2 hat, then what happens? So this would be my minus, this would be the smallest value, and minus, I'm also subtracting y2, minus into minus plus, then what happens? Still I'll get the negative value here. Okay, so here I'm getting the one positive value and one negative value. So I'm just calculating this for this particular point and this particular point here. But if I calculate for all the points here, what happens is, if I want to calculate the sum of all the sum of the difference here for I equal to 1 to n, I want to calculate the difference here, that is y hat minus yi. If I want to calculate this, what happens? So I'll automatically sum up all the values which I have got earlier. That is, I'll sum up, I'll add this positive value, and I also add this negative value, and further we will also get the some positives, some negatives, some positives, some negative. So what happens is all the plus and minus, all the plus and minus will get cancelled each other, and what we are gonna lift I mean what we're gonna left with the value is nothing but the zero. So here this particular zero has no information in our model perspective, right? Zero has no kind of information. So treating, I mean, considering zero would be an absolute time waste. So what we can do is, so if you want to proceed the difference here, so if you want to proceed with this particular method, that is the difference between the actual and the predicted one. So it is actually giving you the value that is zero. So it is not a suitable method. So instead of approaching with this, so what we can do is you need to square up the difference. So how to do that? You'll just square it. Like for example, sigma I equal to 1 to n and y hat minus yi whole square. So this would be the squared value. So why are we actually squaring? Why? Because if we square it, then what happens is all the values won't get cancelled each other. Then we will left with the original values. For example, see here. For example, I have got the positive value, okay, and I'm squaring it, okay, and also I have got some kind of negative value and I'm also squaring it. Also I have got some kind of positive value, I'm squaring it. Also I have got some negative value, I'm squaring it. So what happens? If you square any kind of negative number, it will automatically become positive. So ultimately we will get some kind of value which is the positive one, right? So here we are actually getting some kind of information. Instead of zero, we are getting some kind of information. So this method is okay, but also if you want further what we can do is we can just simply divide this particular sum of the square with the, see, I'll tell you. So sum of the squared I equal to 1 to n, sigma equal to 1 to n, and y hat minus yi whole square divided by n. So what is this n here? What is the n here? So n is nothing but the total number of data points. So n is equal to total number of data points. Okay. So we are actually dividing with the total number of data points. So this is the same. This is nothing but the sum of the squared error, right? So we are actually getting the difference between the predicted and the actual one, and we are actually summing up, and then we are actually squaring it up, right? So this is nothing but the, what we can call it as, this entire thing we can call it as mean sum of squared error, right? So you can call it as mean sum of the squared error. So instead of writing this entire thing, we can shortly write it as MSS, means sum of squared error. So sorry, mean sum of the squared error. So MSSE, you can write it as MSSE. So how to pick any kind of best fit line? So now we have so many lines. See here. See, we have so many lines like this. See, these are all the data points here. Okay. So we need to pick one best fit line out of all the infinite number of lines. So how to do that? We gonna calculate, we gonna evaluate each of the lines. So we will, so first we will go for and evaluate this particular line, and then this particular line, and then this particular line, and then this, and then this. So likewise we will evaluate each of the lines. Okay. And then what is the evaluation metric here? So for which we can decide this is the best fit line. So how to decide that? So the metric here is MSSE. So we will check the line based on this particular MSSE value. So we want the particular line with the least mean sum of squared error. So we will check for the any of the line which is having the least mean sum of the squared error. So if any line has the least mean sum of the squared error, then we will pick then we will pick that line as the best fit line. Okay, so this is the thing here. This is what we can do. And this particular best fit line, I mean, I have explained how to pick up a best fit line, right? So this entire process is done by this process of picking best fit line is done by the method that is the gradient descent. Okay, and also we can also found this best fit line using another kind of method, which is nothing but the algebraically. Okay, we can also find can also do this by algebraically, but but this algebraic method is not a scalable one. Is not a scalable one. So what is a scalable thing, and why we should not use this algebraic method? I'll tell you. But before that, I want to explain one kind of a thing. So just wait. So I'll tell you. So we can see picking the best fit line. Okay, best fit line. Best fit line can be done by two ways. One is the gradient descent approach, and the second one is algebraic method. So algebraically also you can obtain the best fit line. So we will look for this gradient descent only. Why we will not be finding the best fit line using algebraic method. Why? Because see, in algebraic method we can find that by for example, I'll tell you what is an error. Error is nothing but the difference, right? So error is equal to y minus y hat. So the difference between the actual thing and the predicted thing is nothing but the error. So error is not a bad kind of thing. It's just the difference. It's just indicating the amount of difference. So what you can do, y is the actual one, right? So you can write, everybody knows that y is equal to mx plus c, right? Okay, I have written this. So I'm just, instead of writing mx plus c, I'm just written y. And we also know that y hat is also equal to mx plus c. So instead of writing y hat, what I can do is I'll write mx plus c here. Okay. So now the equation is y minus of mx plus c. So this would be our equation. So if you want to find this best fit line, what you can find is you need to find this m and also the c, right? So this m is nothing but our weights, nothing but the slope. C is nothing but C is nothing but the interceptor, right? So now, so this M and C, nothing but this M and C, and this entire line can be found by using gradient descent also. But how in algebraic method, how can you do that? So in algebra, we can find best best M, that is nothing but the best slope. using this particular formula, that is correlation of x comma y into standard deviation of y divided by standard deviation of x. So this is the formula to find the best m, right? So how to find and now how to find out the best c here? So we can find that best c, that is minus y bar minus best m into x bar. See, what is the value of this best m? This is nothing but this particular value, right? So we will get I mean, if we try to substitute all the values inside this particular formula, you'll get some kind of value, right? So that value is nothing but the best m. So we will substitute that particular value of best m inside this particular formula here. So by substituting the value of best m here, we will get some kind of value which is nothing but the best c here, right? So using these two formulas, we can also find the best m and c, nothing but the best parameters here. So what we will get, if we can find out the best m and c, what we will get, you will get a chance to substitute uh, in this equation. For example, let's say I have got some kind of 50x plus 70. So this would be my these are all the two values which I have got when I try to compute best m and best c, right? So this is the best fit line for me. Okay, if I say this is the best fit line for me, yes, you can do this by algebraically in this way also, but we should not. Why? Because this is not a scalable. See, it's not a scalable, not a scalable. That is, what does that mean? For example, we have for example, we are given a kind of data set. Okay, we're given a kind of data set, and here it's having uh, only two columns, that is x1 column and is x2 column. Okay, we need to predict some kind of y. Okay, y column we need to predict. It's pretty much simple, right? It's pretty much simple. Why? Because there are only two columns. But what if we have what if we have some kind of data sets like we have x1, x2, x3 and so on. We also have some x100. So we have some 100 columns here. So what happens then? These are all the columns. That is our independent variables. So likewise, we have 100 variables. Then what happens? So if the independent variables are actually increasing, then and also we have some kind of see here we have only 5 rows. Okay, we only have the 5 rows. But what if we have here some 5 lakh rows? Here 5 lakh rows. So that means here the columns are actually low and the rows are actually low. But here columns are very high and the rows also very much high, right? So there are number of columns and number of rows in this particular data set, but here there are only small kind of rows and columns. So whenever you find a situation like this, then what happens is it is almost very difficult for our algebraic method to find the best fit line, right? Why? Because it takes very long time. It is in algebra, in algebraic method, when columns and rows are increasing, it takes a long time to find our best fit line. To find the best fit line here. Okay, so this is the scenario here. So that's the reason for which we won't be using this algebraic method, right? So that's the thing. And also I also want to tell you one thing. It is very much important. uh See, for example, I have uh so this is our x, right? So this is our y, right? So what is the mean of x? What is the mean of x? So mean of x is nothing but this particular somewhere here in between the middle of x, right? So this is nothing but the mean of x, which is x bar. Okay, and what is the mean of y? Which is nothing but somewhere here, that is in the middle of the y. So this is the y bar here. So our linear regression, I mean, in the linear regression, what happens is our best fit line will be that line which is actually passing through the junction where x bar and y bar met, right? So I'll tell you. So our our uh, our best fit line will be that one which is actually passing through the junction where x bar and y bar is actually meeting here. Okay, so see here it is actually passing through this particular point. So this would be our best fit line. The best fit line will always be passing through the junction of x bar and y bar, right? So this is an important point which you need to remember. Okay, so I have told you one such a metric, like I have told you one kind of a metric, which is the uh, average sum of square, right? That is the mean sum of square. Average sum of squared error. This is also called as mean sum of squared, right? Mean SSE, which is nothing but MSSE also. So this is a kind of metric with which we can evaluate all the lines and we can pick best fit line. And I will tell you another metric with which we can also pick the best fit line, which is nothing but the coefficient of coefficient of coefficient of determinant, which is nothing but the notation r square. See here, r is nothing but r into r. This is not the thing, right? This is the absolute bullshit. So this is not the case. Why? Because we everybody knows that what is meant by r. R is nothing but the Pearson's coefficient, correlation coefficient, right? So Pearson's coefficient correlation coefficient is nothing but the r. So if you multiply, you may think of like this. If we multiply r by itself, then what we will get is nothing but our coefficient of determination. You will think of like this. No, this is the wrong thing. So this is not the case. Okay, so that's not the case. This is this simple kind of a notation. The notation of coefficient of determinant itself is r square. Okay, so it will pick up the best fit line. Okay, and the value, what should be the range of this r square? So the r square value will lies in between 0 to 1. Okay, did you remember r? That is nothing but the Pearson's correlation coefficient. This lies in between -1 to 0 1. I mean -1 to +1. But here, in this case, r square, that is coefficient of determinant, is actually lying in between 0 to 1. So you just need to remember these things, right? Okay, so, and now I'm gonna tell you one important thing. This particular coefficient of determinant, that is r square, will only be true in case of simple linear regression. Simple linear regression. Okay. What is meant by simple linear regression? In which it has a one independent variable and one dependent variable. So this is nothing but a simple linear regression. But R square is not true. R square will not be true for multiple linear regression. Multiple linear regression. That is a that is multiple independent variables and one dependent variables. So the R square will not be true for this kind of a situation, that is multiple linear regression. So how can we decide that? So what happens if the value is that, I mean, if R square is equal to, if R square is close to 0, what happens? And if R square is close to 1, what happens? So we need to decide that, right? That is, for example, if R square is closer to 1, then we can say that our line is closer to data points. Okay, so which is a good thing, right? If our line is actually lying just very closer to our data point, then this is a good model. So we can say if R square is closer to 1, then we can proudly say that this is a good model. This is a good model, right? So if R square is closer to 0, what happens? Our line is far from data points. Our line is far from the data points. So what we can say, so this is a worst model. So this is not the right model. This is the worst model. We can call it as. Okay. So based on the r square value, that is the coefficient of determinant, whether it is, if it is very much closer to 1, then we can call it as the good model. If it is very much closer to 0, we can call it as the worst kind of a model, right? So based on that, we can decide whether our model is good or worst. So this is the thing, and now I'm gonna tell you about all the different kind of errors, right? Okay, so let's see here. What happens is we will try to build multiple models here. Okay, why? Because see, if we get, if you have like this, okay, we will, each line is nothing but a each model, right? So each line is a model. So how many lines are there? See here, there are so many kind of lines, right? So we need to find the best line out of all those. That is nothing but our best model, right? So we need to build all the models here. For example, we need to build so many kind of models here. So for in that purpose, we will be having so many kind of errors here. So I'll tell you what are all the errors now. Okay, so I'll tell you. For example, see here, Okay, so this is the x and this is the y. So what is the, okay, I'm placing it as x and I'm giving it as y. So what is the x bar here? So x bar is this in the middle of the x, which is nothing but the x bar. So what is the y bar here? This. So this is the y bar here. Okay. So uh okay. So what I have already told you that our best fit line will always be passing through this particular junction where x bar and y bar has already met. So this would be our best fit line, right? So for example, if I want to consider as a kind of point here, for example, I want to consider one of a kind of point. I'm considering this point here. Okay, I'm taking this particular point here. So what happens is, if I try to project this onto my x bar, onto my x, so what happens? See here. And if I want to project this onto my y, so what is this? This is my predicted one. That is, I can call it as y hat. Okay, I can call it as y hat. So what is my actual one? What is my actual one? So my actual one is, let's say this, uh, let's say this particular point is my actual one. So how can I project it? So I'll just try to project it here like this. Okay. So now what happens is, this is my actual y here. Okay. So we gonna have some kind of errors here. So what are all those errors? I'll tell you. First of all, I want to name this kind of points like for example, I want to name this point. Let's say P1 here. That is the point 1, and this is the point 2 here. Okay. So this is the point 1, which is nothing but the actual one. This is the point 2, nothing but our predicted one. Okay. So this is our best fit line, which is nothing but this diagonal line. So I want to tell you what are all the errors here. So this particular error, did you see here the entire error, which is uh, starting from the point 1 to till y bar. Okay, this particular thing is nothing but the total sum of squared error. Okay, you can call t as e, total sum of squared error, right? So this is the total sum of squared error, the overall error. And but what did you see here? We have already calculated earlier, we have already calculated that this uh, like what is the difference between the actual and the predicted one, right? So the difference between the actual one and the predicted one here is nothing but the just the sum of the squared error, which is sse. Okay, sse. Just remember these points, I'll try to explain later. And now what is the difference between this p2 to y bar? What is this particular error? What is this error? The difference between the distance between the p2 to y bar. What is this? This is nothing but residual sum of squared error, or yes e, residual sum of squared error, right? Okay, so this is the thing here. Now I'll tell you. So this is the total error, TSSE, right? This is the thing, total. And now when you look at here, this is the residual here, residual sum of squared error. Okay. And this is the sum of the squared error, this thing. So just try to understand one thing very much clearly. Like you have this error, right? That is SSE. That is the distance between this particular thing, right? The distance between the P1 to P2. This is nothing but the SSE, right? So SSE can also be called as unexplained unexplained variance, right? So the name itself is actually saying unexplained, that is, which can't be explained by our model. So no matter whatever may be the thing is, in the linear regression, we can't explain why it is actually happening. Why it is actually the difference between the P1 and P2. That is our actual and the predicted one. Our model can't explain this, right? Oh, sorry. One thing I want to thing is this RSSE, right? RSSE is not a residual sum of square. This is but a regression, right? Regression sum of square. You can call it as regression sum of square, right? So I'm pointing out here. So this is nothing but the regression sum of squared error, right? So regression sum of squared error. And this particular unexplained variance can also be called as residual sum of squared. Residual sum of squared, RSSE. Okay. It can also be called as residual sum of squared. Okay. No matter whatever may be the thing is, we can't even explain how it has happened. I mean, our model can't explain the sum of squared error, which is nothing but our unexplained variance. Okay. So how to decide whether our model is the whether our model is the best fit one or not? How to decide that? So we will decide a model which is the most fit, where every data point lies on the line. That is, if every data point is actually lying on the this particular line, most of the data points are actually lying on the same line, then we can call it as a best fit line, right? So what is the meaning of this? Every point is lying actually on the same line. So I mean, that means the sum of squared error, that is the unexplained variance, is approaching towards zero. It never be zero. I know that it never be zero. Okay, but it can be reduced towards the zero, right? It can also be reduced. We can reduce it, but it can't be eliminated totally. Okay, so in this case, if it is actually approaching towards zero, then we can call it as our model our model is good. We can call it as this is the best fit line, we can call it as. Okay, and also what is the poor fit? What is the poor fit? Poor fit means if this particular uh, SSE is actually far from the zero, right? If it is actually going far, that is, it is actually very much greater than zero, then we can say, I mean, far, we can also call it as far. SSE is far from zero, then we can say that our model is poor, right? So you can call it as like this. And when you look at here, what happens is the SSR, that is nothing, RSSE, that is the regression error, right? So we can also say like this. For example, RSSE, that is regression sum of squared error, divided by TSSE, total sum of squared error, equal to, what happens if I divide this with our total sum of squares? It will be equal to 1. It should be equal to 1, right? So this is the thing. And what happens, uh, this this thing, that is uh, regression sum of square error, and the total sum of square error, the ratio of the regression sum of square to the total sum of square error is also known as, it can also be known as coefficient of determinant. Coefficient of determinant, which we have already seen that nothing but r square, right? So that's the thing. And what if here in this case, if SSE is, that is the sum of the square error, then nothing but this particular thing. If this particular thing is actually far from this zero, then we will say our model is poor. And also besides, if it is far from zero, then what happens? Our ratio, that is regression sum of the squared error, RSSE divided by TSSE, total sum of square, it is actually close to zero. It approaches, and it approaches towards the zero, that is close to zero. It close to zero, right? So this is the condition here, to differentiate between what a good model is and what a poor model is. Okay, so I want to tell you one thing. This is the last thing in this particular session. So I want to draw some kind of thing. Uh, so this is nothing but the y bar. Okay, and this is nothing but the x bar, which is, I have already drawn like this, right? This is the x bar, this is the x, this is the y, and this is the y bar here, right? I have already drawn this, and I have taken some kind of point like this here, right? So this, I have taken some kind of point here like this. So when you project here, what happens is, so this would be your predicted one, that is y hat. What is your actual one? This particular point is your actual one. So this is the y hat, this is the y. So likewise, I am drawing this here. So this is our predicted one. I can call it as predicted one, that is y hat. So this is our actual one, that is y. Okay. So here, if I project this here, I am getting like this. So this is, for example, so I'm just shading here. So this is all the shaded part here. Okay. So this is the shaded part here. So what happens is, the main thing here is, uh, see, our best fit line will always be passing uh, through this particular x bar and y bar. See, this is our best fit line, right? Okay. So here the main thing here is so the distance, like for example, here, see this diagram. The distance here between the actual thing and the predicted thing, actual one and the predicted one is there is some kind of distance. Okay. And what if I have some other kind of diagram? See, I'm erasing this. See here. See here. See, this is nothing but the y hat, right? So this is nothing but the y, and this is nothing but our the x bar, and this is nothing but our y bar. So this particular line is nothing but our best fit line. So how I am saying this is the best fit line? Why? Because see, the difference between the y and the y hat is there is some kind of great distance. Here I'm actually observing great distance, great difference. But when you look at here, the difference between y and y hat, there is very much less distance, right? So this is the main thing. The distance between this particular y hat and y should be uh, as minimal as possible. Then only you can say that it is the best fit line, right? So the percent of total variance that is represented by that particular line, that is the amount of total variance captured by the model, is presented by this line. This is called the coefficient of determinant, right? This particular shaded part is nothing but the coefficient of determinant. That is the R square. Okay. And I want to tell you the basic difference between the R and the R square here. Why? Because that's very much difference, and even sometimes many people will get confused with that particular thing. That is the correlation here. What is the Pearson's correlation coefficient? Nothing but the R. So why do we use R? We use R to find out the uh, whether any independent variable is the best predictor of dependent variable or not. So to find this, we use correlation coefficient, that is R. And what does its range here? The range lies from -1 to +1. And what is this coefficient of determinant here? Coefficient of determinant, which is R square here. This is used to predict, this is used to pick the best fit line. And what is its range here? 0 to 1 here, right? So we before the model building, before the model building has happened, we use the correlation here, correlation thing, Pearson's correlation coefficient, to find out whether there are any kind of good predictor variables which are actually predicting uh, decently our dependent variable or not. To find out that, we use correlation here. And after that, after confirming all our independent variables, we, with the help of those independent variables, we build a machine learning model and we want to evaluate how good a model is. So in order to evaluate any kind of model, we use coefficient of determinant, that is R state, which is 0, which lies in between 0 to 1, and correlation lies in between -1 to +1. Right? So yeah, that's all in this particular video. And now so with this, I hope you have got the great clarity regarding this linear regression model. And in the next video, I'll be continuing this series. So I'm going to tell what is the structure of a linear regression models. So I'll be explaining that. So that's all for this for now. I hope you have got the concepts very clear, and I'll see you in the next video. Just take care. Bye. Jai Hind.